All right. All right, so cold day today, huh? But thank you guys for braving the cold and coming here. So we are going to continue our discussion of linear regression. Um, discussion of linear regression, namely we're going to discuss multi-parameter regression, polynomial regression, and regularization. And then that will round us out. And then next time, on Thursday, we'll start on logistic regression, and yeah, and then that will cover all the basic regressions, and then we'll get to more exciting stuff. Okay, so one day, man, I wish they made a spell check for Jupyter notebooks. Well, they probably do. I should see if I could add that. Okay, so let's begin. Linear classification 2. Let's begin with multi-parameter linear regression. Okay, so last lecture we discussed a lot of linear regression stuff. Is my mic working? Yeah. Okay. Sounding a little weird from up here, but okay. Yeah. So last lecture we discussed a bunch of linear regression stuff, but mostly we kept our discussion limited to single slope parameter, single bias parameter, right? So this is referred to as simple linear regression. Simple as in you have a single. I mean, it's a single line. It's self-explanatory, right? So we could have multiple different types of linear regression. Specifically, we could have multiple parameters, which we fit for, to get a single value. So this is called multiple linear regression. The naming scheme is very clever, isn't it? So what do we do with multiple linear regression? Well, we treat this pretty much the same as we treated simple linear regression, right? Luckily, the way we defined things last time, we defined things in a way that's easily generalizable. So we have a bias term, or this could also be written as m0 times x0 to the 0, or m0 times x to 1 times 1. And then we have a slope term times the first parameter, a slope term times the second parameter, a slope term times the third parameter, right? So looking at this in code, let's say we have a 2D So all of this is just flavor to generate some synthetic data set. We don't need to really do that. But let's say we want to fit a 2D series of code. Namely, we want to fit a plane to a particular data set. What do? Well, we have two parameters, so we need a W2 and a W1 val. We need the B vals, so we have a particular set of parameters which we want to go down the gradient of. And then we have a particular set of parameters we want to go down the gradient of. This requires us to turn the gradient tracking on for PyTorch. Remember that. And then we do pretty much the same thing as we did last time. We have the ground truth values, this is just the synthetic data set plus some noise. We have the ground truth values minus the actual, minus the parameters minus the inputs times the parameters. Then we do the mean squared loss, and then we propagate the gradient backwards. And then we modify the gradient by some learning rate. Again, we're using very simple standard gradient descent. And we're clearing the gradients there. And then we log the information. And so if we zoom out a bit, so we start off with some random points along a 2D plane. W1 and W2 are here. These are W1, W2 are here. These are the parameters. There is some bias value, of course. but these are the two parameters we're concerned about. These are the two inputs, sorry, the two inputs, x1 and x2. And so we start off with a plane that's pretty much close to 0. I've actually found that if you use, going back up here, one of the little tricks I found, if you use mp random.normal, it gives you a value that's usually very close to 0, which makes sense because I'm setting the mean to be 0. So we have a plane that's very close to a flat plane, and then after several iterations, after 50 iterations, it goes closer to the points and closer and closer and closer. So after 500 iterations, this plane looks pretty much dead on to describe the synthetic data set. Now, knowing we generated a synthetic data set, let's see, we could refer to the values. What were the values of the synthetic data set? It was 1, 3, true M2, yep, 1, 3, 3. So if we look at the actual values we get a final guess that's closer to 1, 3.2. Okay, and that's only because we're adding some random noise that biases the data set one way or the other because we have a limited number of points. And so, you know, we don't get exactly what we get with the synthetic data set, but we get something that's very close, especially with the slopes. Yeah, and this is a far cry from the initial guess, which was, I don't know, -0.5, -2, -5, -0.2, -0.5. Okay, does that make sense? So literally, we're doing exactly what we did with the simple regression. We're just doing it with more parameters. Okay. So that works, right? So what's interesting here is that, well, oh, what? Oh, huh. What's interesting here is that literally the same matrix solution that we derived for the optimal fitting parameters from last time for the simple regression, that same matrix solution still works here. And we're going to come back to this matrix solution more in this lecture, but I just wanted to point out that we could still do the same matrix solution as we did last time. It's just the only difference is that now x, instead of being a 2 by, now instead of it only having a column for W0 and W1, now x has a column for W0, W1, and W2. And so x is slightly larger, but all of that is accounted for. So if you do the same matrix math, you get the optimal values, which is fairly close to what you get over here with gradient descent. Okay? So that's kind of cool, isn't it? That we don't actually need gradient descent to do linear regression. We really only need this little term, this little matrix solution, and we could get a multi-parameter gradient. We could get the optimal fitting parameters for a multi input linear model. I think that's kind of neat, right? Yeah. Oh, this was just me error coding yesterday. Oh man. So with all that, one might ask, why not we just do linear regression for everything, right? Why don't we just do linear regression for everything? And let me fix the formatting for this. Come on. There we go. You deserve your own slide, Ali Rosh. All right, so question is, if linear regression, it works, at least it has been working for our synthetic data sets. It works for a lot of data sets, actually. It works for a lot of data sets. The question is, why don't we linearly regress on pretty much everything? I mean, especially if we have an analytic solution, right? That's kind of the nice thing about this, is that we have a pure analytic solution that for a fitting model, which is not that common, right? So why don't we do that? So let's look at a more complex data set, and let's look at a real-world data set. I want to introduce sort of using real-world data sets a bit, because eventually you're going to have to use them. So one of the neat things about Python, one of the neat things about, Python, is that you have all sorts of libraries, and mainly you have the scikit-learn library that has a whole bunch of data sets preloaded with it. So it makes loading some of these data sets very easy. And so with the scikit-learn data sets, this is like a classic data set. There's a classic California housing data set that basically gives you the housing prices of California homes. I think this is from years and years ago. I think probably in the 90s. It was created, I'm pretty sure it was created in the 90s. It's roughly 20,000 entries. And it gives you the price of California housing given a bunch of parameters. Now it gives you the house value given the median income, given the house age, given the average number of rooms, average number of bedrooms, population, that the population density, I should say, that the house is in, the average occupancy, latitude, longitude. Gives you a bunch of like little factors, and so you can play around with it and actually evaluate how much a house way back in the 90s was. So for some of these things, it does seem like linear regression might work, right? So especially for median income, which kind of makes sense. With median income, the median house value seems to, I mean, there's a huge variance. There's a huge variance here, but the median house value does seem to range linearly with the median house value, which makes sense, right? Richer people get bigger houses, and really, I mean, the standard piece of advice I think that people give you is that your mortgage shouldn't exceed more than 30% of your income. So, I mean, that is a linear function. So that would make sense. Now, there are other factors that seemingly have no real pattern, namely house age, average number of rooms, average number of bedrooms, population, average occupancy, latitude, longitude. This is by far the dumbest parameter that they collected. I don't know why they collected this parameter. Because guess what does anyone want to look up the latitude and longitude of San Diego? Look it up on your phone real quick. I looked this up last night, and yeah. Oh yeah. Who has it? Yeah, please. 32, negative 117, so like right there, yeah. So this would correspond, and right there. So this would correspond to like the San Diego, I mean, I spent summer in San Diego. So this corresponds to the city proper, and this corresponds to the areas north of the city that all the good companies are in, like Broadcom and everything. All the rich people are there. And same thing here. San Diego, slightly north. So so San Diego's there, and of course these two big spikes correspond to San Francisco Bay Area, right? So really, latitude and longitude don't really tell you anything. And trying to fit a linear model to these parameters is actually pretty terrible. The gradients are horrible in this case. I'll show you guys what I attempted. It wasn't successful, but I will show you regardless. So I did the same. I did the same gradient descent. Doesn't let me go past. Okay, whatever. It's doing the same gradient descent. You have initial guesses. You have a multi-parameter model, and usually when we do the gradient descents, you get some values. But of course, in this case, you get some absurd numbers like negative e to the negative 20, e to the 27, and you get not a number. This happens when basically integers and floats overflow. The gradient just doesn't work. When you try to fit the data to a linear model, the gradients become absurd, and you end up getting garbage out. Okay, and it sort of makes sense because most of these things are not linear. Most of these things are not linear. They're barely, these things aren't linear. This only thing that might be linear is the first metric, which is median income, which, granted, is the first metric right there that actually does sort of work. Oh, no. Yeah, 0.5. Median income, the house value is 0.5, which actually makes a good amount of sense. Yeah. It actually makes a good amount of sense. The rest of these are absolute garbage, especially the latitude and longitude values, which makes sense. So linear models aren't always appropriate. And most of life is not linear, especially when you're gathering stupid variables like this. So play around with this data set. I'd be interested to see if you guys could figure out a good fitting model for this. Well, there are plenty of good fitting models online. You could look up some research papers. But yeah. But the major point of all of this is to say that linear regression models aren't always perfect. So what do? We don't want to lose. We really don't want to lose like sort of the analytic solution. We don't want to even lose like the linear fitting model, right? Even if we didn't have the analytic solution and we had gradient descent, it still works well, the gradient descent, right? We just want to be able to fit more robust models, more complex models to the data. So in that case, what do? There we go. In that case, what do? We look at something that's not linear. Namely, we look at polynomial fitting next. Okay? So let's go back to our synthetic data. We could leave California behind us for a couple lectures. It'll rear its these well-known data sets will come back. We'll come back into view, but for now we could go on to we'll just have good working examples for ourselves. And let's have a synthetic data set, which is something like this, right? Now, looking at this data, a linear model might not be the best here, right? This doesn't look very linear. We could probably fit a line that goes something like this, or something like this. Oh, maybe that would be a better fit. But it won't be ideal. Why? It's because we, being intelligent human beings, having the nice little pattern recognition engine in our brain, we could see that this is working. This is more like probably what the data is describing, right? So it's describing some polynomial function, so it's describing some polynomial function. So the question is, can we fit a polynomial function to this data? Oh, the linear model. So this is the optimal linear model. Again, not ideal. It's not horrible, actually, given all the terrible models we've seen, the terrible fits I've seen. Not the worst fit in the world, but it's not optimal, right? So what do we do in this case? Well, we think about the last couple lectures. We fitted way more complex models than those linear models to the data. So I guess we'll just have to do that again. Namely, a complex polynomial is simply the combination of a bunch of powers of x, right? So if we can combine linear functions together, why not combine polynomial functions together also? So let's try to do that. So we do this. So combining polynomial functions together, or combining any number of functions together, is what is done using what we know as a feature map. So what does this remind you of? This little vector of polynomials. You've seen an abstraction of this before in one of the lectures. Yeah, please tell me. Yeah. Well, I mean, basically when we were all doing all the matrix calculus, right? I was telling you guys that let's suppose we have a function that is a vector of functions, and then we do all the derivatives and all that matrix calculus. Well, this is sort of what it was all for. Well, not all for, but this is one of the reasons it was for. One of the reasons why we did all of that, because we basically have this concept of a feature map, and all the feature map is the combination of a bunch of different functions. And so with polynomials, with polynomial fitting, the feature map is simply a combination of a bunch of polynomials like so. And then we can simply make the regression model the parameters, the fitting parameters that we will modify and optimize for, times the feature map. Okay? And doing this allows a lot of things that we did in the previous lecture and in the previous lecture to remain the same. We're going to come to that in a minute. But let's just look at how the feature map would work. Namely, now we have a one input system, and we have a feature map. We have a one input system and a one output system. And so let's define our feature map again. This is, again, just to generate the synthetic data right here. So let's, yay, okay. So let's define a particular order. Let's say order 3, which means that we have all polynomials up to and including x cubed. And let's simply say that the fit is simply a bunch of a bunch of weight inputs, times. So the 0 weight input, this is the bias, plus weight 1 times x to the 1, plus weight 2 times x to the 2, plus weight 3 times x to the 3. Okay? This is literally just the polynomial fit. I just wrote it a bit generally because just to make the code a little bit more generalizable for later, for our discussion later. And so we have a gradient. We have a bunch of weights, a gradient, which we need one weight for every polynomial plus the bias, right? So for order 3, i.e. we need a weight for x to the 3, we need a weight for x to the squared, we need a weight for x, and we need a weight for just the bias term. So we need order plus 1 weights. And of course, we'll set the gradient equal to true, telling PyTorch keep track of this variable and any functions that work off this variable. And then also we do the same thing that we did before. We calculate y, which is simply the sum of the weight times the x to the I for all I in 0 to order. And then we calculate the error between the predicted value and the actual target value, which is our synthetic theta. And we calculate the squared loss. Okay? That. Okay? And to do the update step, instead of doing the updates, as WGD equals negative alpha times WGD, we simply do WGD is equal to WGD plus the velocity, where the velocity is equal to the momentum times the previous velocity. Yep, the momentum times the previous velocity plus WGD times alpha. Okay? Now, one important thing, maybe one side note I want to take here. Why didn't I do this? Velocity and why did I do that? Times momentum plus or minus alpha and I'm gonna comment these out again before I forget, because it does break the code. But why didn't I do this? Why did I go through and do all of these? Do all of this? Yes, please. Yes. Okay. Good. Good. Patrick, right? Yes. Okay. Good. Just wanted to make sure. Yeah. So Patrick, I mean, clearly you've been messing with PyTorch a lot. So I think you've run into this. So this is like one of the big mistakes everyone at some point makes when they first learn PyTorch, is that when we do this, what we're doing is basically allocating new memory, like a new data structure. Like when we were doing this part, allocates a new data structure, and then we're assigning that new data structure to WGD, which isn't the worst thing in the world. But when we allocate the new data structure, we're not turning on the gradient requires true. And in fact, the new data structure is separate than the previous data structure, right? So if we do this, if we do this after one iteration, basically the WGD that we allocated here, that we turned the gradient on for, that sort of goes out into the ether and sort of disappears, and therefore, and PyTorch basically complains that you can't do that. So when you wanna actually update a particular value, with the gradients over a for loop, you have to use all in-place operations, which is why I used all in-place operations here. A little annoying, but that is why you have to do that. And that's also why the torch.nn library exists, because that will take a lot of this hassle. The optimizers will take a lot of this hassle away from you and basically optimize your code so that you don't have to do everything in in-place operations. Just a nice little side note, I wanted to point that out because those of you that are experimenting with this already, you might run into that issue. Okay. Anyway, so this time around, so we're doing the same thing. We're calculating the mean squared loss. We're calculating loss. We're assigning the loss equal to the gradient. We're calculating gradient of the loss, and then we're modifying the fitting parameters according to that loss times the learning parameter. And in this particular case, I did do the momentum method for the gradient it took a lot of time to get this code to work. The more complicated the models, the less the less cooperative PyTorch becomes. Well, it's not really PyTorch's fault. It's math. Math is the real villain here. But the more complicated the models, the more complicated your learning function, your update functions have to be. So that's why if I did just the standard WGD minus plus alpha WGD, it would not work. It would not converge very well. But anyway, good thing we have the momentum method because we update the gradients and we get some final guesses. Okay, so looking at before, the underlying function was 0.25, -0.5, -10, and 20 for the parameters. And if we actually go through this process, we get 0.25, -0.47, very close to -0.5, -10.05, very close to -10, and 23.78, very close to 20, or was it 25? Either way, very close. It was 20. Okay, so it was 23. So a few off of 23. So works pretty well, I think. And also, if we actually plot out the regression function, you see the line that the model guessed, the actual function that the gradient regressed to, and the data points. And I think everything is pretty much spot on, right? Probably a better fit than the ground truth model that we had previously, thanks to the variation of the noise that we input into the synthetic data. Make sense? Okay, good. So I think that's kind of neat. That, you know, the same thing, gradient descent is pretty robust, although again, you probably need the velocity, you need the momentum a bit to stabilize it. I just get tired of constantly writing that, so I always try to do the simple approach first. Okay. Why? Okay. There we go. Okay. So what I always find interesting is just viewing how the function changes over time. So again, we could view how the function changes over time over the, I think I put it for 200,000 iterations. Again, it's the more complex the model, the harder it is to get it to converge well. But that's what we learned last time with our discussion of primal optimization. Working with the gradients becomes more difficult. The more uneven the principal axes become, which is very true in this case. The principal axes are uneven because we have one value that's 20, another value that's 10, another value that's 0.05. All those principal axes, just from that, the principal axes of the different dimensions are uneven. So it makes convergence a little more difficult. Yeah, but again, as we see, the function starts off at just a random guess, and this is pretty much just, I mean, x cubed plus x squared plus x plus 1. I think this is roughly the values there. It's just a normal third-degree polynomial, standard third-degree polynomial. And then as we iterate on it, it slowly gets the Hayden curve. It slowly updates the x parameter and the x squared parameter to get this rise and dip, this humpback. And then you obtain the final results like so. Kind of neat to see the curve evolving over time. All that makes sense? Okay, so what's nice about polynomials, the polynomial fitting, is that we could still get a matrix solution to the polynomial fit. And the key to realize is that this isn't really, we didn't really do anything different than the linear regression case, than the multi-parameter linear regression case. We had the same matrices, but we just defined it a slightly different way. So let's go through and define the polynomial function as a series of matrices. Namely, we have a particular polynomial function here. We have y equals the fitting parameter times 1. This is basically the bias b, times m1 times x to the 1 times m2 times x to the 2, m3 times x to the 3, all the way up to mn times x to the n. And as we know, x is the independent variable, y is a dependent variable, and m0 through m1 and m and n are the coefficients of the regression model. Why are you being dumb? Oh, I know why. There we go. So, are the coefficients of the regression model. And so, we could redefine the system as a model for each data point. Namely, data point 1, y1 is equal to 1 x squared all the way to xm times m, m1, m2, mn. Oh, this should be, I screwed something up.
I think that minus m should be mn.
Yes, yeah. Oh. X1, yeah. I didn't think I double checked this one especially. Oh well. So we have y1 is equal to 1, x1, x squared, all of this, multiplied by m0, m1, m2, and up to mn. So the major thing is we take all of this, and then, so 1 gets multiplied by m0, x1 gets multiplied by m1, x2 gets multiplied, or x1 squared gets multiplied by m2. That gives us this function here, and we say that's equal to data point 1. Same thing, data point 2. Same thing, data point 3. All of this down to data point n. And this, we rewrite this as y is equal to m times x, right? Same thing as we did before, except the one difference here is that before we would have 1, x1, x2, x3, x4, x5, x6, x7. Over here, instead of all of that, we're just doing 1, x1, x1 squared, x1 cubed, x1 to the 4, etc., right? So instead of x2, x3, we're just doing x squared, x cubed, etc., Okay? And yeah, so x2 in this case is effectively x squared. So we define this matrix like follows, and then we do a similar optimization that like we did before. Namely, we want to calculate the loss. So we want to calculate the minimum arguments for W, where the ground truth minus y squared is minimized. The sum of all these data points is minimized. Then we can rewrite this a little bit more. Y is of course equal to x times w. Then we could rewrite this in terms of matrices, get rid of the summation sign. Basically, t minus x times w squared, we want the argument of that. Then we expand out this squared. So we simply take the transpose times the normal vector of all of this. And then again, we expand out this whole term, and we get these matrices here, this expression here. The ground truth transpose times the ground truth minus the ground truth transpose times x transpose w minus w transpose x ground truth plus w transpose x transpose w. Okay? So this is all just basic math we're doing. And then we want to find the minimum. We want to find where we want to find the point where the loss is minimized. So we basically take the gradient of the loss and set it equal to 0. And doing that with respect to the weights w, of course. And doing that, we get this whole thing disappears. This is not a function of w. We get this term stays because it's like a linear term. It's like ax, the derivative of ax with respect to x. You just get rid of the x and you keep the scalar. So we're keeping the scalar here. Same thing for this. We're keeping the scalar, and same thing here, except here we get a factor of 2 because w is in this twice. Okay? Effectively, we have w squared. Yes, please, Anna.
Can we get rid of the transpose instead of like give w transpose x transpose w, and then when like you kind of treat that as w squared, and then when you're taking down the 2 and getting rid of the square, why are you getting rid of the transpose version of w?
Ah, okay, good. You could actually keep the w here. You could actually write this as wx x transpose 2. It would give you the same result. Yeah, matrix math. You could do multiple ways to get the same result, but it does work out. Yeah, but yeah, good question though. You could do either. And in fact, this formulation is slightly different than the formulation that we did last time in lecture, and this is slightly different than the formulation in code, and I'll point that out when I get to it. But you can flip around the transposes and get the same thing. And so we get rid of this term, we modify these terms to take the derivative, and so we're left with an expression that's equal to 0 of, we're left to this expression that's equal to 0. We do a bit of finagling. We combine these two terms. We move it to the other side. And then we multiply both sides by x transpose to the negative 1. To the negative 1. There we go. And then we get the matrix solution for w as x transpose x to the negative 1 times, we get the matrix solution to w as x transpose to the negative 1 times x times the ground truth t. Okay? And this is actually slightly different than the formulation we got last lecture. Namely, last lecture we said x transpose times x to the negative 1 times x transpose times t times t. And so it is different, but it's also pretty much the same because the transposes, the x transposes, are just flipped around. And flipping them around and doing this consistently gives you the same value. Okay? Does that make sense? It's kind of neat that all of this works out. As long as you're consistent, the matrix math will work out. It's like multiplying the whole thing by 1. Okay? Or putting it, or I should say, it's like making the exponent to the 1. But in this case, I think the dimensions of w will be transposed also. But really, that doesn't really matter to PyTorch. PyTorch figures that away, which is always nice. speaking of PyTorch, we could do literally that in PyTorch. Instead of doing the whole gradient descent, we just have the order, and we calculate x. Namely, we calculate this x matrix by saying x is initially, first column is all ones, then next column is all x to the 1, second column is x squared, third column is x cubed, right? All we're doing here is basically starting out with a column of ones, then adding a column of x's, then adding a column of x squareds, then adding a column of x cubes to keep our formulation in line with how we formulated the problem here. So we have that little bit of code to properly formulate the x matrix. We don't really need to do anything to t. And yeah, and we have everything we need to calculate the optimal w, namely the inverse of x transpose x times x transpose times t. And if we actually plot that out, we get a particular tensor that's 0.25, negative 0.54, negative 10, 0.28. This is different than what the gradient descent gave us. I think gradient descent gave us something different, especially for the bias. I think the bias is somewhere around 24. This is around 28. But this is the optimal point, the optimal analytic point. And actually, if we plot it out, we see that, yeah, this does look pretty optimal. I mean, we can't really judge by just looking at it, like, oh, that's optimal. We don't really know just by a picture if something is mathematically optimal. But given that the picture looks pretty good and that we've calculated out this matrix solution, we've reasoned out this matrix solution from here. It's pretty convincing that, yep, we have the optimal formulation there. Make sense? So that matrix solution also works for polynomial fitting. I think that's interesting. And what's more interesting is that we could do it for more than x cubed. We could do it for many different degrees of polynomial. Namely, we could do it, since there are 10 points, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This actually got cut off. The equation here got cut off. There is an x to the 9 term. There is a bias term. There's a y equals term here. But the title got cut off a bit. But as you see, if you could always fit a order n-1 polynomial to a data of size n perfectly, right? Like you could, because it's like a system of linear equations. You have a system of, you have 10 data points and you have 10 unknowns. So doing that, you could fit a function perfectly to the data, but this is what we would refer to as a overfit. Do we believe the ground truth data, the underlying model behind this data to look like this? Probably not, right? This is just the computer doing what the computer does, which is doing what we asked it to absurd levels of conciseness. And so we have to pretty much, a lot of human intuition has to come into play here, which is we have to determine how complex the model should be for a particular data set and work from there. Does that make sense? Yeah, but the code is there. You could try fitting. You could try fitting models of different. You could try fitting models of different. Orders? Yeah. You try fitting models of different orders to the data. See what the models come out to. You could try using different data. Again, by just modifying different data by modifying this x, different order and different polynomials by just modifying this parameter to see what you get. Kind of fun. And it was very hard to get working, so I hope you guys enjoy it. Play around with it. Okay, so That's good. That's polynomial regression. Basically the same as linear regression, except we just have to modify the x per x matrix a little bit, as we showed. And then, of course, we could combine polynomial regression with multivariable regression. That might be a good, that would have been a good homework problem if we didn't already write the homeworks. But we could also combine those two things together using just a bit of help that way. Okay, all that makes sense? All right, so last part of the lecture, regularization. So let's look at some more synthetic data, namely, let's look at the synthetic data model here. And if we look at the synthetic data, we have what's pretty consistent line. If we were just to draw a line here, we would probably do something like so. Probably be pretty close to something x equals -1. I mean y equals -x, something like that, because we have y is -10 at x equals 10, and y is 10 at y is 10 at x equals -10. So the true fit line, or maybe the ground truth line, as we would see it as human beings with great pattern recognition brains, is probably somewhere around y equals -x. But we have noise in our data. We have noise in our data. Specifically, we have two big jumps and variables here, and the computer likes to consider all data is equal. It doesn't consider outliers. We're not actually calculating outliers or anything yet. We're just calculating, we just have this big jumps, and the computer is trying to fit everything. And because it's trying to fit everything, it's just increasing the bias to sort of minimize the loss between these points here and matching it to the loss between the line and these points here. Okay? So, not great for a multitude of reasons. The biggest reason is that usually when we are trying to fit machine learning models, when we're trying to fit models to data, we've gone through the step of making the data largely consistent. So in this case, largely even, right? One of the best things we learned from primal optimization is that if the principal axes for the loss are uneven versus the parameters, then gradient descent doesn't work that well. So of course, one of the best things that you could do to make the principal axes more even is just to scale the parameters, right? That would make the loss, instead of an ellipse, it would make it more circular, right? So we could sort of do that here. The loss function for the underlying function is more circular because the underlying function is y equals -x plus 1. So that's a pretty circular loss function because the parameters m and b are roughly equal. They're on the same order of magnitude. Unfortunately, because of these two noise, the computer made the parameter for b significantly larger than the parameter for n. Okay? We don't want that. Let's say we knew that our parameters are roughly equal, and we won't want the computer to skew the fit towards one parameter or the other. Okay? So, stopping the computer from favoring different parameters, from skewing the fit to one parameter or the other, is what's known as regularization. Okay? And regularization works with linear regression very well, which is why we're discussing it in this lecture. So, regularization is simply the idea. That we can encourage the model to normalize parameters, to minimize one parameter getting pulled a particular way. Okay, to minimize one parameter basically becoming solely responsible for the output, for the predicted output. And so, in order to do this, there's multiple different types of regularization, but the most common one that we're going to talk about in this lecture, well, not the most common one, but the most basic one, is what's known as L2 regularization. And what L2 regularization is simply a penalty term in the loss function where this lambda is a fitting term, but basically we take the square of all the weights and sum them up and just add them to the loss function. Okay? So what does this do? This basically tells the loss function that if one of the weights is significantly greater, then that will cause this square term to blow up, and that'll increase the loss function. And remember what we're trying to always do. We're trying to minimize the loss function. We're trying to make the loss function as small as possible. So if we're trying to make the loss function as small as possible, this is a bad thing. We want all the weights to be as small as possible. As small as possible, and we don't want one weight to be huge and one weight to be small, because even though that one small weight won't do much, that one huge weight will scale polynomially. Okay? And so our goal, so the computer has this new loss function, and the computer's goal is simply to look at these two losses and try to find the way to the minimum here, and also to try to find the way to the minimum there, and find the point at which the minimum of these two matches. Okay? Namely, another way to visualize this is that if we overlay the two losses on top of each other, this is the L2. The blue is the L2 loss function. That's very circular. That makes sense because the contribution from each one of those parameters is equal with the L2 loss. And we have the linear loss function to the data that is ellipsoidal, again, because we know the slope has more of a significant impact on the loss than the bias. We want to find the computer has a point, has a loss, and it wants to find its way to the minima, both to this L2 minima and to this L1 minima. Now, we can't do both. It can't go to the L2 minima because then it'll increase the linear minima, because then it'll increase the linear loss. It can't go to the linear loss to this point here. You see these red contours. This is the linear gradients. Can't go all the way here because then the L2 loss is increased to a point. So it has to find a medium point. It has to find a particular contour where the L2 loss matches the linear loss. And basically at this point, the computer is pulled two ways. It both wants to go, it both can minimize the loss by going to L2. It can minimize the loss by going towards the linear minima. But if it does either, it'll increase the overall loss because, again, the whole loss function is mean squared error, right? So going one way increases the loss for one more than it decreases the loss for other. Okay? So visualizing it this way, hopefully it's clear why this is known as ridge regression. You're trying to find a particular ridge. So you have this ridge here, contour here. You have this contour here. And right where it meets, right where those two contours meet, that's the ridge that you're trying to find your way to. That's the minimum point. That's the new minimum point of the whole function. Okay? So in this case, what do we do? Well, we could do the same. Gradient descent algorithm and get the loss there. Or another thing we could do is do the matrix solution again. So what do we do in this case? We simply have a new loss function. We have y minus xw squared, and then we have the gradient loss. We have the L2 regularization loss, the regularization penalty, I should say. And so we take the gradient, we set the gradient equal to 0. We get rid of the two constants. We get rid of the two terms. We have this lambda times w term. And again, remember this lambda term is the fitting parameter. And so we go through this math. We go through this math like so. And eventually we get to a point where we see that w is equal to x transpose x plus the lambda times, this is the identity matrix, inverse, plus x transpose y. Okay? That is our new loss function. And so, that's all well and good, but let's see how it works if we test it out. If we actually test this out, namely, if we construct our x column like so, basically in this order we have just an order 1 function, and we're just, so basically we have ones, a column of ones, and then a column of just x's. We have a new lambda parameter, which is, we're setting it to 0 now. So if we do the matrix multiplication solution, we get the following figure, which is the same as what we saw before. That's good. That's our control. Lambda is equal to 0, so we have no L2 regularization loss. So we have no L2 regularization loss, so we don't need to really, so nothing changes. So the good news is the matrix solution that we've developed with the regularization, it works as if lambda is equal to 0. Now if we make lambda equal to 10, no. Nope, wait a minute. Wait a minute, I know what's going on. Where is the polynomial? It's a string function. There we go. Forgot to run that all. There we go. Yep. Go back. There we go. Now, if we make lambda equal to 10, we see the line go more towards the other values here. We see if we make it equal to, let's just make it equal to 50. Oops. What happened here? I don't even know what happened there. Yeah. Let's just make lambda equal to 50. Then we get something that's pretty much bang on these other values. That's bang on the other values, and we've minimized the effect of the spikes, right? So we haven't completely eliminated the effect of the spikes. These are pretty much outliers. So the only way to minimize the effect of these is to pretty much get rid of them by doing some outlier computation, which we'll discuss later in the course. But the regularization helps because it is basically forcing these parameters to be smaller, to be more equal to each other, and to be smaller in general, right? Because the L2 regularization loss penalizes large parameters. Now, that's great. The only issue is that if you go too nuts with this, then you get a situation where you're basically just forcing that you're just having the L2 regularization become the primary component of the loss. And what happens there? If the L2 regularization is a primary component of the loss, then you just get a flat line, right? So that's not ideal either. In fact, it's very much not ideal. So just something to think about. So L2 regularization is useful, it's especially useful in multivariate linear regression, assuming you format your data so that everything is scaled fairly consistently with respect to each other. L2 regularization is very important there. If you take the Andrew Nick course on Coursera, he has a good data set with L2 regularization that highlights its importance. It's a little involved though, not good for a lecture. Um, but um, but anyway, but you could use, but it's useful in a variety of contexts. And what's more important, I think that the most important thing that I wanted to put across is that modifying the loss function of bits, like so, still allows you to get a closed form solution for the optimal weights with linear regression. Really, that's the beauty of linear regression, is this closed form solution that you don't need to do gradient descent with. And so, something to remember. Something to remember a lot. Okay, so so that about covers L2 regularization. I think that's it for today. We're going to discuss logistic regression next time. And yeah, stay warm. I'll see you on Thursday.